title was chosen to connect computational intelligence, or maybe it's better to say today machine learning, машинное обучение. We could also say artificial intelligence, искусственный интеллект, but this term is seen a bit outdated now because traditionally artificial intelligence was a bit different thing. So to connect машинное обучение, machine learning, and uncertainty in modeling. A couple words about myself. Those who understand English know it. Так что я по-русски скажу. Я в институте IHE Delft for Water Education, Institute for Water Education, and we don't have вот уже сложно. Bachelor programs, but only master programs and PhD programs were located in Delft. We have 200 staff in total, and we have 180 MSc students starting every year, and we have in total 120 or 130 PhD students studying at any given moment. And we also have additionally 600 people going through short courses, so that's what we do. So we have 15,000 alumni, because our history is 60 years, so we have a lot of alumni. We have 4 master programs running with many specializations. This is too quick. Delft is a nice city. Okay, I will move on. This is the Netherlands a bit. You see that rivers sometimes flow above sea level, above ground level. And if you take a bike from Delft to the North Sea, you would go through a point which is minus 4.6 meters below sea level. And then you go up a bit to the sea. So that's quite complex water management history around this. That's why Dutch engineers are known to be experts in water management in general, and they are sort of enjoying being recognized indeed still to be top of the line. It's not in all areas, but in many areas this is the case. Now, what is hydroinformatics? I'm working in the chair group of hydroinformatics. The term was coined by Michael Abbott, who was the author of the book Computational Hydrological. He was one of a not very big group who in the 60s and 70s developed methods to solve water-related differential equations using numerical methods. So and that was called computational hydraulics, or вычислительная гидравлика. And his book was translated to Russian as well. But in the end of the 80s, he thought maybe we should move to something else to extend horizon, and he coined the term hydroinformatics. By the way, in his book, he says informatics comes from Russian word informatika, and he's even writing it in Russian. But of course, it's French origin, but I don't know why. Maybe like Dimitris points only at Russian scientists. Mike Abbott was also somehow fond of Russian scientists. And hydro, obviously water, so we define hydroinformatics as modeling, information, and communication technology and computer sciences, so much wider than just numerical methods, applied to problems of aquatic environment with the purpose of proper management. So we try to look at different things, at data, models, and humans. So we'll try to integrate all of it in one technological discipline. I wouldn't say it's a science, but it's a technology. And essence in this technology is integration. So we'd like to integrate all possible data sources, remote sensing, human observation, citizen science, gauging. If this is hydrological load, then we would, if this is observations plus numerical weather prediction models, this would form hydrological load. So for example, in the problem of flood management, we have to know all this, and then we would use models to run forecasts coming from prediction models to generate hydrological forecasts. So modeling plays a very important role here for sure. And then we also involve citizens, because citizens are final consumers of modeling results, plus stakeholders, because if you want to make decisions, you have to involve stakeholders. So we're also looking at problems how to actually organize discussions with stakeholders so that they would accept results of modeling or results of forecasts. Because very often stakeholders are conservative, water management, who studied 20 years ago or more, and often they're constrained by their also political considerations. So it's also important way to use models in order to convince decision makers. And then here you see the word probabilistic. So more and more during last 10 years, maybe we are looking also at account of uncertainty, of which you heard a lot already. So in order to, before we start talk about uncertainty, I would like to have a quick start into using machine learning for rainfall runoff modeling. So that's a traditional problem in hydrology, to map rainfall into runoff. So if you know rainfall, you want to know what will be runoff now, or maybe several hours later, or maybe several days later. So this is an example of Sievi catchment in Italy. This is 3 months hourly records of flow and rainfall. So problem here is to build a model that would relate rainfall to flow, so that we could then simulate this process. Come on, this button. So traditional way would be to use lumped conceptual model, or maybe distributed model if you have data, like what we did on Monday. This is this model, HBV, actually, here represented. Another way is to use data purely. So this is what we call data-driven approach. We do not assume that we know much about the processes here, but if we have enough data, and here you have 2,000 records, so it's quite a lot of data. So using this data, we want to build a regression model that would calculate flow at the next time step using all data that we have up to now. So this is all past data. Past data about rainfall, these are lagged rainfalls, you see T-1, T-2, and so on, and lagged flows. So this data we have. So why not to try to build regression model here, F, this regression model, that would link all the past data and try to calculate what would be happening now, or 1 step ahead, or maybe 6 steps ahead. Data-driven name says модель, основанная на данных. Это означает, что мы в основном используем данные, а не понимание физики. Хотя без понимания физики такую модель трудно построить, хотя бы потому, что нам надо знать, какие лаги здесь использовать. So, well, this is repetition of what I said, actually. Now, let's look at simple data-driven model. Forget about rainfall runoff for a second. I want now to talk about this model. Well, imagine this is rainfall and this is runoff. And you collected 11 points, 11 records to represent this relationship. This is empirical data, data which was observed. So if I press a button, yes. Oh, no. If I press a button quickly, yes. So look, we're building now a linear regression model here. You see we're optimizing parameters A0, A1 by solving optimization problem. This problem is shown here. So I want that distance between each point to green line is minimum. It's an average distance. Well, I don't divide by t, but I could. It doesn't matter because it's minimization problem. So this is observations, yt at each time step. There are 11 time steps. And this is the model. So I want distance between observations and the model to be minimum. That's purpose of every modeling exercise. So I built such a model, as you see, linear regression model. And now, if new data of x comes in, I could use the model to calculate y. Okay, so then this model encapsulates all the data that we have, 11 records, into one simple green line, simple equation. То есть это уравнение в себе содержит все данные, которые у нас были, в виде очень простой функциональной зависимости. Это и есть самая простая data-driven model, линейная в данном случае. Так, какие здесь переменные decision variables? Here there are 2 decision variables. It's single variate model, A0, A1. How do we find these 2 variables? We solve optimization problem with respect to A0 and A1. These are unknowns, all the rest is known. These are measured inputs and these are measured outputs. See? The problem is ill-defined. Why? Because it may happen that you have many more data than parameters. So it may happen that you may have to choose different parameters, and still they would give you similar results. But okay, that's another problem. So this is what we do in modeling. We try to build a model. Oh, somebody's calling me. No. It's my computer? Sorry, I'm sorry. It seems I'm connected to my corporate account. Sorry for that. I'm busy. You cannot see. You can see only.
Take your time.
You mean I have to answer the call and have half an hour conversation with the director or something? Now, let me show you example so that you would. Just a moment. It doesn't move. I don't know what's happening. Well, now let me show you the simple rate forecast model that we will build now together. It was working in the break, isn't it? Now it doesn't. So look, we will now open this data set, which was about CAV catchment, and we will now build a simple model. What we'll see now is, can you see it, more or less? No? Not much? Anyway, let's run the movie. So we will now see the process of building the red model based on green data. You see the red line wobbles around green data. So idea is that the green line, the red line would eventually be very close to the green line. Green is runoff, which was measured. Red is what model says, model's output. Okay? And now, as you can see, through the optimization, red line is getting closer and closer to the green line. It's like in the linear regression model, I was trying to fit the green line. Here I'm trying to fit red line to the green. Okay? So that's an example of using the data-driven model, neural network in this case, to try to reproduce relationship between the rainfall and the flow. Sorry, I'm getting back to. Now, exercise for you. So wake up so that you would wake up. Now, I would ask you, I'm building now a model to represent this data-driven model. First model I propose is linear model, which is green line. It has an error, you see? Every point is not exactly on the line. It means for each of the measured points, model gives an error. Not good. Because we agreed that good model is the model without errors, correct? So error ideally should be 0. Dimitri doesn't agree, but I'm considering extreme case. Okay? So it's nice if a model, since model is replication of reality, модель это представление реального мира, хорошо бы, чтобы модель была как можно ближе к реальному миру. Now I propose another model, red one. It has a bit smaller error here, because it's getting a bit closer to the blue points. Disadvantage is that it's second order model, so it has 3 parameters instead of 2. So it's a bit more complex model. Немного более сложная модель. But if we agree that the model should have 0 error, I would propose now the blue model, which would have 0 error, and tell me if it's good or not. This model has 0 error because it goes through all the points. It's a spline model, so it just goes through the points. So error is 0. Is it a good model? Why not? Какой процесс? Too many parameters, yes, too many parameters, so what? But you're right, if I add one more point, model would be very inaccurate because it does something wrong. So I think the best model here is red because it picked up the trend. Green is also not bad, even if it's so simple. Blue model is too complex, and we say it overfits the data because it goes through all the data collected. If we collect more data, it will not go through this new data. So it will have on the new data higher error.
In my view, the green is better.
Perhaps. It depends on...
Why? Because if it is second order, the red one,
yes.
If it's second order,
yes.
At some time it will turn down.
That's true. Good point. Yes, you're right. But if we consider this as an interval for the whole data set, then it's fine. Okay, it's illustrative example, obviously. So I have to find the balance between complexity of the model and its accuracy. And the model should not be accurate on training data, on calibration data. It should be accurate on out of sample case. So look, when we're improving the model from this is green model, this is red model, and this is blue model, it has 0 error. Complexity goes up. So our complex model has very low error, but it will have high error on validation dataset, which in machine learning is called out of sample dataset. You see, so when we start increasing complexity of the model going this way, errors would go down, down, down. Error on calibration set would still continue to be going down, but error on validation set or test set would go up at a certain moment. So you have to choose this complexity. It would be a balance between complexity and accuracy. Okay, so that's theory. In reality, it's much more complex, but it's good to know the theory so that in real life, your experiments would follow more or less this idea. Right, now how to choose input variables. I have shown you 11 input variables in this rainfall runoff model, or 9 actually. We could show them without running the model beforehand by using either correlation coefficient. So correlation coefficient would show the dependency between different variables, inputs and output. It's good to have high correlation. If correlation is low, then strange why we should use this input variable. То есть коэффициент корреляции должен быть повыше желательно. However, coefficient of correlation shows dependency between 2 variables, and there are many. And it's also linear. That's why we use, as Dimitri suggested, information theory. So it would be better to use this information theory or average mutual information criterion. There are other versions of it to judge about relatedness between different variables and output. Because it's good to have variables with high relatedness to the output. So in our case, when we look at rainfall, this is rainfall and this is flow. You see there is a lag here. If we look at the plots here with the zoom tool, you would see that lag is varying between 3 hours and 7 hours. So on average, if you calculate average mutual information, you would find out that optimal lag here is 6 hours approximately. This is when average mutual information is maximum. So it means you have to put into the model the lagged rainfall, and lag should be 6 hours. Because this catchment reacts in 6 hours after the rainfall. It's not fully true, of course, because if rainfall is close to the outlet, but in Russian... Замыкающий створ, абсолютно точно. Спасибо. Если у вас осадки близки к замыкающему створу, то реакция будет мгновенная, а если они далеко, реакция может быть будет 10 часов. Но в среднем, если брать aerial average rainfall, average lag is 5 hours. So that's a way to choose inputs for your machine learning or regression models. There is more to it, but this is enough for the time being to understand. So for the time being, we considered linear model as linear regression model. Now let's look at, again, at neural network. We already have shown you how it runs, but now let's look again at the neural network. So artificial neural networks. So there are many types of neural networks, and I should say some of these methods, as Dimitri said, are not really neural networks, but they were sold as neural networks because it's easier to get research funding. In the 80s, in the United States, 70% of research was going to neural networks, like now to climate change. So if you want to get research funding, rename your method into a neural network and you get it. It was then, not anymore.
Now rename climate.
Now it's climate change is in fashion. Maybe there would be global cooling in 20 years in fashion. We don't know. But at that time it was like this. So many methods were, books were written, professors were... Good question. So вопрос для интерполяции или экстраполяции. Да, data-driven всегда интерполяция, но если она умная достаточно, она может и экстраполировать. Но недалеко. Физические модели, естественно, экстраполируют далеко, потому что они знают физику. Эти машины знают только данные, которые были собраны, поэтому они не могут далеко экстраполировать. Okay, let's move on. So this is standard multi-layer perceptron neural network. And it didn't start from Kolmogorov's papers, no. It started from an attempt of some scientists to replicate human brain. Idea was when computers appeared in the 40s, they said, oh, we know more or less how human brain works. It consists of very small neurons. Let's imitate them by computers. And if we have many neurons, we'll imitate human brain. How many years later? It didn't happen yet.
They haven't read Kolmogorov, that's why.
They haven't because it was in the 40s. Kolmogorov hasn't written that paper yet. So neural networks started before Kolmogorov, sorry. For that strange case, Kolmogorov was not there yet. But indeed, later, research in neural network was influenced by his paper because they said, look, we have theoretical justification. Of what? So look at the neural networks. These are inputs, input signals. These input signals are distributed to green blobs. Each green blob is a linear function here plus nonlinear term. So it's a linear regression model here in each of these plus nonlinear. So first we apply a linear combination of inputs here. You see this? A linear combination of inputs. And then we pass it through nonlinear filter like this here. So it squashes the signal into 0, 1 range. And here it's linear, in fact, and here it's nonlinear. So that's standard function which is used in MLP neural networks. There are many other functions, but this is standard and widely used. It's only in one neuron, but there are many neurons like this. In each of them, you have exactly the same equation, but weights are different. These coefficients are different. Okay? Now, output neurons work in a very similar fashion like this one, very similar fashion, but coefficients are different. So what you have here, you have combination of many small, simple functions. Inside linear, here slightly nonlinear, but when combined, it forms very complex nonlinear equation. So it's simply nonlinear regression equation with many unknowns, A's and B's here. This is neural network. That's it. So this is called hidden layer, this is called output layer, and you can see this neural network may have many outputs. That's a nice feature, so you can immediately put quite complex problems with many outputs. But typically, we use only one output, because it works, in fact, better. Otherwise, it's confused by too many things to model. Any question about this? So that's MLP network. Now, how do we find these coefficients, which are unknowns? We find such values of weights, this A and B, so that brings error of the neural network to a minimum. Error is different distance between observed and measured squared. It's typically mean squared error is used, but you can use other forms of error also, no problem. Okay, that's biological motivation of neural network. Okay, fine, let's skip this. This is hidden node, as I explained, in fact, already. First linear term, and then it goes through nonlinear, and this is output. And this is output node, which is similar things. Transfer function is this. It's a logistic function with a simple equation. This equation is nice because it's easily differentiable. And more, when you write the derivative of this function with respect to u, you can express it through g itself. So derivative can be expressed by the function itself. So it's very nice feature because it simplifies computations, especially in old days when computers were slow. Now look, this illustration that using these simple functions, these are the sigmoid functions you see in these nodes, but if combined, you can model, as you see, very complex function here. So just illustration from a textbook of Smith. So he shows that, and if you combine more, you can imitate quite complex functions. So that just shows how neural network works. Now, how to find the minimum of the error function? It's very complex function. So you have to solve nonlinear optimization problem. This is the function to minimize. So this is a difference between output of the network, which is Z, and measured value, which is F. So if you sum it up, these linear terms, nonlinear terms, in the end, I need the battery here because it's now low. Yeah. So the laser pointer doesn't work anymore. So you look at the last line. This is the function to minimize, and decision variables unknowns to find are A coefficients and B coefficients. And how many of these to find you have? Quite many, so it's a complex problem. You have number of coefficients, which is number of inputs multiplied by number of hidden nodes, right? Plus number of hidden nodes multiplied by number of output nodes. That many coefficients. It could be 400 coefficients easily to find. So how to do it? Fortunately, these functions are differentiable. So it means to solve optimization problem, there is no problem. You can use traditional gradient descent methods, and there are codes written for it. So this problem is not a problem anymore. So you just use standard codes. You minimize the function which is on the last line here, and you find the coefficients. Now, really, it would be nice to show you output, because I want to demonstrate how a neural network can approximate sine function. But I wonder, would we still make it run? No? Yes? Or it works now? You think it works? So what we will do now? I will now close this and we'll start. I will open neural network again. And what I will load now is this example with 79 examples. So we have here one input, which is x, and two outputs, which is sine function and cosine function. Of course, there are no functions. I generated data in Excel, generating 79 examples. So first output is sine, and second output is cosine. So this is first output. You see 79 examples. This is output here, and this is input. And this is second output, which is, what is it? Cosine function. Like this. So this is input, and this is output. So this neural network has two outputs, which is quite exceptional, but okay, why not? 79 examples. So now we will train the model, and let's choose number of weights, hidden nodes, which is 1. I will show you how neural network looks like. So we have one input, which is variable 1, and one hidden node only, and two outputs. So how many weights should we train? You remember we have three terms, which is A0. This is A0, and this is A1. So this is not input first thing, it is three terms of regression equation. So how many weights do we have to train? Question to you, wake up. Сами, sorry? Сколько весов нам тренировать? Но они все на рисунке. Считать надо. Сколько? 6 весов. Это регрессионная модель с 6 неизвестными параметрами. Мы сейчас решим оптимизационную задачу, такую, что эта сетка попытается дать output, выход, близкий к двум выходам, которые я вам показал. Okay? Let's try. So green line is first output, second output is not shown, so let's look at first output. So that's it, the neural network is trained. After how many iterations? Sure? Iterations, 330 iterations, it's trained. Error would not improve anymore, would not decrease anymore. Not terribly accurate as you see. By the way, it is just logistic function. So that's what it is. Now, if we test it now on 12 other examples, you see on some examples it's okay, but on many examples it's bad. So green is verification data. There are in total 12 verification examples to compare to, and results are not very good. So let's increase number of hidden nodes. 2. Neural network now looks like this. We have still one input. We have now 2 hidden nodes, you see here, and we have 2 outputs. Okay? How many ways should we find now? It's a more complex model. So 2 by 2, 6, plus 2 by 2, 4, 10 ways. Instead of 6, we're now finding 10 ways. So let's train the model. Come on. Okay, not going well. You know why? Because it's stuck in the local minimum. It's a non-linear optimization problem. We're stuck in local minimum. I have a button shake. What it does, it adds 10% randomly to each of the 10 weights. Let's see. So it's a random jump in this 10-dimensional space of parameters. Shake again. Oh, look, it improves. It improves. No, so my algorithm is not optimal. So let's stop here.
How much times do we need this procedure?
To shake? Well, in smart algorithms, it's trained in fraction of a second. This algorithm I wrote based on some codes. It's not optimal. So you may never train it well, but this software is not ideal. Now let's increase number of hidden nodes to 3. Let's look at the neural network now. Look, how many should we train? So it's 2 by 3, 6 plus 12. 6 plus 4 by 2, 8. I get 14. Now, 14 weights. Look, it's better now. It's better. So error is going down. See, error not anymore. So error is stabilized. So I think neural network would not improve. It found more or less final solution. This is training. So let's verify. Oh, not bad at all. Look, it's verification set. So it seems that it's enough to have a model with 3 hidden nodes. But let's now go extreme and add 5 hidden nodes and see what happens. So now neural network looks like this. 5 hidden nodes for only one input. It's overkill. But let's train. It will be a perfect fit, I can tell you. So this, you see 5 hidden nodes with many small functions allow you to approximate sine function. Okay? In fact, if I return back to rainfall runoff model, sorry, did the wrong thing. Back to rainfall runoff model with 6 inputs. If we look at neural network, this is the neural network. It has 6 inputs, you see this, which are rainfall now, 2 hours ago, 4 hours ago, 5 hours ago, back, and current flow, расход, и расход 1 час назад. And this neural network predicts расход на 1 час вперед. У нее 5 этих спрятанных, как это по-русски-то, скрытых nodes, hidden nodes. So let's see how it goes. So it's a complex network. Total number of weights is quite considerable. This is 7 by 5, 35 plus something, so it's 50 weights, I think. So let's see how it's trained. So green line is output. There is 2,000 examples. You see, it's a very big data set now. And gradually we move in the space of 50 weights, every time calculating error and calculating this hydrograph. And as you can see, hydrograph is approaching the green line. But this algorithm is not terribly stable, so it wobbles around because steps which I make in gradient descents are too big. So I'm jumping around the minimum, actually. So more sophisticated algorithms that you find in Python and MATLAB would do a much better job. Okay, stop. So you see, not bad. So training is almost perfect. You can reproduce peaks here, you see. This one, not really, but all others, not bad. And this verification. Okay, not ideal. Here it's underestimation, but top peak is almost well reproduced with a bit of phase shift. But that's how it is. Any questions about this model? So this is rainfall runoff model using nonlinear regression equation in the neural network. And we're able to reproduce mapping from rainfall to runoff. Right, so let me see. Good, Shift F5. Yes, it works. That's nice. Now, 2 words about how to. So what is shown here is simply the way to optimize weight. So this is current vector weights, either 14 or 56 weights, sometimes 400 weights. So it's a vector of weights. This is current vector weights at time step 1. Sorry, not time step, excuse me. This is iterative scheme following more or less gradient descent. So this is number of iterations in search for optimal weight. So this is now and this is next iteration. And what we look at is a gradient. So we're following a minor gradient. Because gradient goes up and we want to go up. So this is pure gradient descent. More sophisticated algorithms use also second derivatives, if you can calculate them. So that's all working quite well, so that's no problem at all. Now, sorry. Somebody Shift F5 maybe could press, please. I want to show you the tools. Shift F5. Yes, thank you. This button is a bit sensitive. Right. So I mentioned only 2 machine learning tools: linear regression, okay, machine learning, okay, statistical anyway, and neural network. Okay, MLP, only one type of neural networks. But there are many other tools which are listed here, which work sometimes better than MLP networks, sometimes worse. So if you want to build data-driven model, try to use several, at least 2-3 methods, because it doesn't mean that one would work for all cases. So I just listed here a couple of tools which could be useful. Veka, it doesn't require coding. This is from University of Waikato in New Zealand. People started already almost 20 years ago to develop this tool, and there are many, many different algorithms implemented. It's a bit limited in functionality, but to start, this would be ideal to start for many people, so that's very nice tool. Okay, Python has a special scikit, which is developed mainly on French money, and it's open source, and its last 7 years it's been under development. Not everything is there terribly reliable, but it's moving towards the industrial quality software. This is MATLAB, more reliable stuff, because you have to pay for it, of course. Toolbox for neural network costs $400 if you want to, or you pay 100 rubles on the market, perhaps, I don't know. And there are other commercial tools which have software which is really industrial quality, but then you pay thousands of dollars for these packages. Okay? So, that's brief introduction to machine learning. Any questions? So this type of networks, Professor Chang was showing you yesterday. He was using neural networks, but also Cajonin networks, which is a different thing. Cajonin networks do not, or SOM, so self-organizing maps. Self-organizing maps is not regression model. It is a model that finds clusters and data. So it's yet another machine learning task to find clusters and data. Yet another task, which is very important, is classification. So it's currently used in airports. They would look at your face and would recognize face compared to millions of photos in the database and find out will they allow you to enter the airplane or not. Or they recognize classification, probably read the license plate numbers. So if you're speeding with the car, you would be immediately fined. So these algorithms are very well developed nowadays. You have cars that drive themselves, and they solve all the time classification problems. They classify, is it a pedestrian that crosses the street, you have to stop automatically, or it's a bird flying, or it's nothing. So that's solving classification problems. Right, so.
What about deep learning?
Okay, deep learning is a term which was coined for neural networks with many layers. Okay, why it is needed? It's not for this type of regression problem. It can be used, but no need, because they have many, many weights, and we don't have that much data. So number of parameters in the model should correspond to a number of data points, right? So if you have 1 million weights and 100 data points, something is wrong here. Okay, so you don't need it actually. So deep learning is used mainly for classification of images, where you have millions of data points, because these are pixels or groups of pixels, and they work very well. So there are different classes of these algorithms. So deep learning means simply you have deep networks with many layers of hidden nodes. That's it. And there are different versions of it, and they're optimized for imaging. So for example, one of our MSc students now, she's from Singapore. They have a problem that they have radar images that move, and they want to forecast the moves of radar images. So she will develop convolutional neural network that would, based on past data, how radar images move, they would be able to predict 15 minutes to 30 minutes ahead where the rainfall system would move based on radar images automatically. So that's intention. I don't know if she does it in 6 months, so I'm doubting, but she's so capable. So that's one of the problems where deep learning convolutional neural network may help for weather forecasting. It's a direct impact on weather forecasting. That's amazing results, amazing, if it works. In Hong Kong, they published a paper in 2015 where they show it's possible. So it's very fresh, very new. Okay, yes, but I have another presentation.
Yes.
Not the end, we have yet another presentation. But question, please, yes.
Present the following. If you use data graph election, you have different predictors, different physical.
Predictor output, you mean, in the model?
No, predictor.
Inputs.
Input.
Yes, sorry. Yes,
But between predictor can exist
correlation. Yes. Good point. Yes, in statistics we try to find variables which are unrelated. Okay, and that's theory. In practice, difficult to do. So of course you can do PCA, find the principal components, find variables which are less related. You can do PCA. Yes, you can do. So you have many variables which are related. You do principal component analysis, and you find orthogonal variables, and you feed them in. Possible, but often that's not needed. So these tools are blind and stupid. It's just machines. They would generate outputs unrelated to the fact that these predictors are correlated. So it's so-called approach in data analysis, which cares much less about statistical properties of the inputs. We don't investigate if they're Gaussian or not. Sometimes it's useful, but very often not. We just throw data. Important is to find variables that reflect physics well. That's important. It's much more important than to struggle to make them uncorrelated. Because rainfalls in consecutive time steps, of course, are correlated. That's clear. So that's a lot of correlations. But again, if you want to avoid this, PCAs would build orthogonal vectors that would be used.
Orthogonalization.
Orthogonalization. Yes?
You said these tools are stupid. How can they learn if they are stupid?
Well, even stupid people can learn, But it doesn't mean they will come up with new ideas. They can read books and follow the book, like this. That's neural networks. They cannot, they are not good extrapolators. So clever people are extrapolating beyond books, right? Same here. They could extrapolate by 10% maybe from the things they learn, but not more. So if...
do they really learn?
They do learn, yes, because they learn on the examples we collected. They learn how to represent these examples in the form of equations, like I have shown, okay? In the form of computer programs, let's put it like this.
They fit equations.
Huh?
They fit equations.
They fit equations.
Is that learning?
It is learning, yes. Yes, because you know that if rainfall is high, flow is also high. Kid learns, if it sees something red, don't touch it because it may be hot. So a kid learns, first he touches the cat, because she would never touch it. She also knows it's hot, don't touch it. So, девочки никогда не дотронутся до горячего чайника, они знают, это горячий. А мальчики 25 раз дотронутся, а потом они выучат, что не надо касаться, пальчики обожжешь. So, good question. So, mainly neural networks are good interpolators. So, if data about floods, about extreme floods was not in their training set, neural networks cannot predict extreme floods. But if this flood which is coming is in the range of the data which they have seen before and learned, then it can predict what would be the flow or whatever. Okay, so now what we want to do is to use neural networks to predict not the flow, not discharge, не расходы будем предсказывать, а неопределенность этих расходов, то есть ошибки в расходах. Мы будем предсказывать PDF, как-то probability distribution functions. Плотность, а? Да, плотность будем. Плотность, чего плотность распределения. Вот это мы будем предсказывать. Но до того, как мы туда пойдем, мы сначала давайте поговорим about uncertainty first. So where does it start, this uncertainty? Francesca yesterday talked about this. Today, Dimitri talked about this. Everybody is talking about uncertainty, and I will talk about uncertainty, but briefly, don't worry. So uncertainty is defined as lack of certainty, but if you look at certainty, it's defined as lack of uncertainty. So that замкнутый круг, vicious circle, but fine. I wouldn't go further into this. Now, if we look at simple conceptual model, do you recognize this model? How is it called? HBV, very nice. ХБВ, можно сказать, да? Вот. Inputs are uncertain because rainfall is not measured accurately. States in the model are uncertain. Well, states I'm not sure, but because of inputs they also calculate. Of course, we use deterministic equation, so okay, maybe it's a question. But for sure, parameters are uncertain. We don't know parameters well. How do we determine parameters? Through calibration, right? Calibration is trying to fit the model output to measured data. Is measured data certain? No. if measured data is not certain, we calculate parameters based on difference between measured and calculated. It means parameters are also uncertain. More, in this model, you cannot measure them. In distributed model, you use measurable parameters, here not. So that's even more uncertainty. And model structure is uncertain, because model structure is very simple here. So simplification is always bringing in uncertainties, right? So all of it is highly uncertain. However, model output is deterministic. So this is flow that I showed, and model output is also similar to this. It's deterministic. Question is how to move to uncertain output. So what we see here is gray line. So for each time step, what you get is interval here between two gray values, right? So that's uncertain output. So this interval is in fact distance between 5 and 95% quantile, or maybe 25% and 75% quantiles. So that's why it's gray. But in fact, at each point you have distribution here. This is uncertain output. So how do we account for uncertainty? Let's have a look. What are the methods? So if we look at uncertainty analysis, steps are, we first identify sources of uncertainty, as we discussed. We quantify the uncertainty. For example, coming up with the distribution or range of parameters, which is very difficult because we don't know what this distribution is. So we make some assumptions, as Francesca has shown. This highly influences the results of analysis of sensitivity or uncertainty. We want to reduce uncertainty, of course, in the end, if possible, or maybe not. Maybe uncertainty is part of the model and part of the exercise, so we cannot reduce it, and maybe we shouldn't. Then we study propagation of uncertainty through the model, for example, by Monte Carlo simulation. We'll talk about this in a second. And then we quantify uncertainty in the model output. For example, we analyze the output of results. And we apply uncertainty information in decision making. That's also a critical point. You know why? Because many managers don't like uncertainty. They say, okay, I'm an engineer, tell me, water level will be above 5 meters tomorrow or not? If above, I will evacuate people. If not, I will not. And you say, well, you know, it could be 5.1 plus minus 0.7, and there is a distribution like this around it. He said, fine. Of course, and he will be right because he wants answers from engineers and not just wobbling around some strange values and saying it's good science. So, okay, some people disagree, but this is what managers say. Some managers are educated.
Yeah. For example, I read there is an interesting article from the Netherlands where they interviewed some managers in
Yes.
flood operational services in the Netherlands, and one of them actually they were saying that they would prefer to have some uncertainty ranges because otherwise they have to do this work themselves. Because they are not stupid, they know the model is not right.
Yes.
So if they are given a point value, then they have to figure out based on their experience and reasoning, okay, maybe this is now 12, but could be from 10 to 15. And instead, if this is included as an output of the model, so some, just to say, not all managers are unhappy with uncertainty ranges.
Yes. I'm sure that manager followed our courses in Delft.
That's
It
why.
depends on how smart they are. If they are smart,
Yes.
they need to know the uncertainty. If they are not smart, perhaps they are perfect managers.
You're right. But look, I tried to make a provocative statement and now you disagree with me. That's good. This is what I wanted. Indeed.
The Dutch managers.
Dutch managers, yes. But look, I talked to Spanish professors and they in Spain, it's not like this. But look, it's not about, there is no general opinion. Of course they know there is a reasoning. On my another presentation, I have a citation from a manager in the United States who said, if I would have known that it's not 10, but 10 plus minus 2, my decision would be different. It's citation. So you find different examples of this. What I want to say, that traditionally engineers are asked to give numbers, but now time has changed, because indeed some managers may require to give numbers. If not, then engineers should push a notion of uncertainty into decision-making processes, because decision-making cannot be based on accurate estimates, because all models are wrong, and there are some that are useful. Okay? Все модели не верны, но некоторые полезны. То есть обязательно в принятии решений необходимо учитывать неопределенность. Source of model uncertainty. Okay, we discussed this already. So here, this is the model output, deterministic model, plus you have some epsilons, which are additions or subtraction, maybe multiplication, but we have additive law here. Anyway, it doesn't matter much. So this is parametric uncertainty, input uncertainty, output uncertainty, structural uncertainty, different types of uncertainties. So there is observational uncertainty, so we discussed this already, I said that. Now measures of uncertainty. You can use different measures. You can use traditionally probability distribution, okay? So this is observed river stage, for example, and okay, anyway. Or you can use, if you cannot talk about distribution, maybe you should talk about intervals. So this is your hydrograph, and this is the interval which may represent 5 and 95% quantiles. But inside there is a distribution, of course, which often we don't know. Or you can use fuzzy characterization of uncertainty, as Dimitri said today. Also possible. It's yet another way to describe uncertainty. Размытая логика тоже может использоваться вместо теории вероятности. So propagation of uncertainty. So what we assume, if this is y caret is model output, this is input, this is parameters, this is the model. Okay. Now, so if you have uncertainty in parameters, it should propagate to uncertainty PDF. PDF is плотность вероятности выхода. Или если uncertainty, or if uncertainty is in inputs, it also propagates to the output as well. So how to do this propagation? How, if we know or can estimate uncertainty of inputs or parameters, for example, how can we propagate uncertainty into output? Problem is, if you know this model, you cannot propagate PDFs through the model. You can propagate inputs, which are real numbers, but you cannot propagate PDFs, probability density functions. You cannot. So you can do it only if model is linear, then it's easy. Or you linearize models, also possible. You can do local linearization of a model, and then it's sort of simple. But in more general cases, you have to sample. Simply, you instead of PDF, you get real value. You put it through the model, run it through, and you get output. And when you do it many times, it's called Monte Carlo simulation. Okay? So that's a way to, it's a numerical solution of propagation of PDF. Okay. Have you been there? It's not Monte, sorry, it's Monte Carlo. Sorry for that. Okay. Oops, oh, that was quick. So look, Durgalal made this video. So what it is? It's a real model HBV of Bagmati catchment, I think, one of the events. This is hydrograph flow. So it's HBV model. You see these parameters are from HBV, max, bus, K, FC, and so on. So we sample. So for example, FC is sampled from the interval of 130, 180 using uniform distribution. Now, alpha is sampled using normal distribution or close to it, and you see more samples are in the middle because this is high probability. The triangular, and again, so each model run is based on 4 numbers sampled by 4 generators. Okay, so we generate a vector of parameters, put into the model, run once, and what we get is one hydrograph. Then we sample here, 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 put into the model, run second time, we get this. Here we're running 100 times. We get 100 spaghettis. For Chinese students, it's called noodles. And now how do we study uncertainty? We go to this time moment 30. We have this ensemble over here of runs. These are real values, and using these real values, we simply draw empirical distribution over here, or frequency diagram. And this is your estimation of uncertainty of calculated flow, discharge, for that particular moment. So it's not uncertainty of the model as a whole during this whole past moment. No, it's uncertainty for that time moment, because uncertainty here would be different. So every time step, PDF is different. That's a bit of a problem, and it's not often discussed. because they talk about model uncertainty, but of course, if you take the whole hydrograph and you calculate uncertainty, you can get some PDF, but would it be valuable or not? Not really, because for low flows it's very low, for high flows it's very high, and if you get some average for peak values, it would not be correct representation of uncertainty. So I have to look at uncertainty for each given moment or for each hydrometeorological situation, because every time step or every situation, uncertainty is different. So based on this idea, we developed then a method that would calculate PDF for any given moment in the future, for any given hydrometeorological situation in the future. But about this in a second. Okay, we discussed this. So this is what yesterday was presented, and this is what by Francesca, and this is what traditionally is done in uncertainty analysis. Again, I would like to repeat, uncertainty analysis is typically study of propagation of either parametric uncertainty in parameters into the output or propagation of the input uncertainty, like rainfall, to the output. So, for example, in your climate studies, you may take rainfall, which is of now, or last 10 seasons, you push it through the model and you calculate hydrological response, right, of a catchment. You calculate flow. And for climate studies, you say, okay, rainfall would be perhaps 20% more, or 50% more, then you generate, by using rainfall generators, another rainfall events, you feed it through the models, and you look at the output. Or what you do, you generate many inputs like this, ensemble of inputs, you feed it through the model, and then you would see many outputs, and then you build up PDFs, and this would reflect uncertainty of hydrological situation in the future, when assumed rainfalls would be different, when you know PDF. Dimitri said maybe they will not be different, or maybe we don't know if they will be different. Of course they will be different, but which way we don't know. Yes, exactly. So, but we have to be prepared, right? So we could play with these different uncertainties of inputs for the future and see what happens. Okay, would our dikes be high enough in case if rainfall is 20% more? This type of studies are important, of course, if we want to save lives. So now let's move on with Monte Carlo. So Monte Carlo is indeed sampling inputs, as I showed, or parameters, and running the model many, many times. But we would like to return back to uncertainties. And I said there is also uncertainty in the structure of the model. And structures are typically not sampled. So maybe we forgot something. But let's recall back when we use deterministic models. So before doing uncertainty analysis, what I would like to say that we should study residual errors and uncertainty. What is this residual errors? So let's look at the model M. And let's think that this parameter set is calibrated. So, калиброванная модель, и у нее есть оптимальные параметры, которые мы нашли путем калибровки. And we're using this model as the single model to generate output. Question is, if this model certain, I say it's optimal because it cannot be better. We used all the data available, all the knowledge. We set up deterministic parameters, some values, and we say this is the model. It's a representation of reality. But is it certain? Answer is not. It's not certain because it has errors, as any model. So I would say if it has errors, it means it's uncertain. So there is hidden uncertainty in any model. Maybe I'm using the word uncertainty now in a slightly different sense than we talked about input uncertainty and parametric uncertainty, but still it's uncertainty. We're not certain about model output, hence we're uncertain. So even if, since every model, even optimal calibrated and the best possible model has errors, it is uncertain. So we call it residual uncertainty. So we did everything possible to improve the model, still we have residual, остаточная неопределенность, когда мы уже все сделали, улучшить модель, она уже прекрасно работает, все равно есть ошибка, это есть остаточная неопределенность в этой модели. So let's have a look. So this is actual data, this is measured, this is model. Actual we don't know. We know only measure. There is measurement error here, right? So maybe I have a line. Yes. Now model says this for that time moment. We calculate flow, for example. Model says this, measured was this is model error, and this is observational error. Okay? So if we know observational error, maybe we could correct it. Fine, then we have to update observations with respect to observation error. But let's assume this error is small, and we believe what is measured is reality. Then model to be close to reality. So this is called model error, and we're now saying that uncertainty of an optimal model M, optimal means calibrated, the best possible model, is manifested in the residual model error. It's this error here, this one. It's model output minus measured output. So this is calculated discharge, расчетный сток, а это измеренный сток. Или water level. Okay, this is the residual model error. And we say that this error incorporates all uncertainties due to observational error, inaccuracy of estimated parameters, inadequate model structure, and whatever. So now, when we have this uncertainty, let's try to understand how we can predict this uncertainty. So let's forget for 10 minutes about Monte Carlo completely. So we're not adding additional uncertainty by sampling parameter from PDF. We're not doing this. We have one single optimal model, and we assume it has uncertainty manifested by this error. We'll add these parameters later. So for the time being, on this escalation of uncertainty analysis, as I called it in somewhere in EGU, I think, and building up model uncertainty. We start with residual uncertainty of an optimal model, and then we add uncertainty of parameters, data, structural, and uncertainty of a model class. So we could move it like this. But for the time being, let's be here, and this is where we should start actually. So before we move to PDFs, we agreed that model uncertainty is in the error. Question is, what is this error? So let's look at this picture, which I already explained. So we have a physical system, we have a model. It's process model, hydrological model, for example. So we get input data like rainfall from the physical system. We identify parameters somehow, put it into the model here. We have observed output. So we are now running model for the past data. Мы прогоняем модель для прошлых данных, для которых у нас есть измеренные значения стока. So we can measure error comparing observed output and model output, and this is model error. Okay, this is error written up here. It's from previous slide. Just we use Q instead of Y. Ошибка модели, разница между вычисленным значением расхода и наблюденным. So model error. Okay, this is how models work. But since we now know what machine learning is, let's do this. What we do this is we will build neural network model here or regression model that would forecast the error. Question is it possible? Well, why not? Look, for the past data, not for the future, but for the past data, we would have model error. For the future, we don't know because we don't measure. Yeah? So for the past data, we would have model error. We would have rainfalls, including previous rainfalls. And we would have model errors. We will have model output and also previous model outputs. So we have a lot of data. Like we're building hydrological model using past data about rainfall and flow, in a similar fashion, we can build a data-driven model to forecast error of the model M. Because we have enough data in the past model runs. So this model would encapsulate the error. It would be regression model, could be even linear regression. Like bias corrector. You know, bias corrector, it's this thing. Bias corrector looks at previous errors in the model and just in an arithmetic sense, or maybe a bit more complex, it corrects model output. It's the same thing. Simply here, we want to build a bit more sophisticated model using all available data here. So when we train this data-driven model to forecast error. Now we put these two models, hydrological and EM, which is error model, into operation. And if new data comes in, rainfall, model would calculate model output. Okay, this one would take previous values because they're available from rainfall and flow and model errors, and forecast the error. And then we subtract error from the calculated runoff, and we get improved output. This is so-called error correcting scheme.
So it's not about uncertainty, it's for improving output.
Yes, not yet uncertainty, so we purely improve output. So this is deterministic, all deterministic so far. It's all deterministic. Okay? So the model is deterministic. This model is deterministic. Here what you get output is real value. It's deterministic, no PDFs yet, nothing. But error manifests uncertainty. But it's not yet represented in the form of PDF, not yet. Next step. Okay, is this clear? Any questions about this? So again, we train this on the past data. We calibrate this model, train on the past data, then we fix it, and then we put it in operation. So in operation, this model would forecast error, and if you subtract it from calculated discharge, you would get improved output.
Well, one could argue that if the model is good, the forecast error should be zero.
You're right, but we agreed that no model is so good that error is zero.
Yes, but we use the same type of model.
Yes, so if...
Data-driven model.
Yes, well, no, but this model is not necessarily data-driven. It could be anything.
That case, yeah.
But look, if this model has zero error, this one could be trained to generate zeros here, of course. Because every time output was zero, so it will generate zeros here. So your data-driven character would say 0, 0, 0, 0, 0 every time. So error is zero. Because it's trained on zeros. So it's no problem. But again, this is traditional model. This is process model. You see? Process model. So that's hydrological model. Okay, good. Now we move on. Okay, this is single model run. Okay, we discussed this. Now, no Monte Carlo. We agreed about this. Forget about Monte Carlo. Again, I would like to repeat. No Monte Carlo. Now we start talking about uncertainty without any sampling. So how can we now reduce residual uncertainty? We want to build a model by analyzing past data and predicting residual error. So we simply collect data about residual error. Yes, we discussed this already, sorry. Next step is to... Sorry, it's the same slide. Moving slides, it's almost the same slide. I want just to say what is the typical error character model here. So error at the next time step would be a function of, for example, previous rainfalls, soil moisture in the model. We can, by the way, take soil moisture, which is a state, from the model. We cannot measure it. But trick is that this model may have soil moisture, which would be useful information to calculate error. So it's additional thing. So it's a hybrid model, in fact, because this one may take data from inside the model, soil moisture, and also the flow. Okay, we discussed this. Let's move on. So what I say, to have the error value forecast is good. However, what if we want the distribution of the error? So we don't want the error now numerically. What we want is the PDF. Okay? So, well, this is flow, but if we subtract calculated flow from measured, you would have PDF of the error. That's what we want to build a model, and then if we have this model, we will be able to assess model uncertainty for the new inputs, that is for the future situations. So let's see how we can, yes, okay, that's what we want. What we want is, this is analysis and this is now. And what we want to have PDF for the future. Not only model output for the future, this blue blob, but also PDF around it. That's what is model forecasting. So how can we do it? I propose simple method now. What we can do is this. We take this is error now, not outflow, this is error, you see? This is time. So we calculate error for each time moment, and we build simply empirical diagram here, frequency diagram, and this gives you quantiles of this error, isn't it? 75% quantile would, well, these quantiles, these are quantiles, would give you the estimate of the interval in which error would lie. But it's based on the data, on the whole data set. So it's not characteristic of every hydrometeorological situation. So, okay, maybe we could improve. Yes, by the way, model conditional processor of Tadini, which is propagated around the world, and also other similar work, do similar thing. What they do is this. This is a figure from his paper of 2008, model conditional processor. I advise you to read it. It's all good reading of Tadini's things, but if you look attentively, you would see, so density here, he builds the density for simulated discharge of 18 cubic meters a second, you see? It's a conditional density. So we assume, so this is whole data set across years, or across the whole year. So we put all this data set on one plot. Then we say, what would be the distribution of observed discharge when we get simulated discharge of 18. So imagine your model runs. It says discharge is 18, okay? And using the whole data set, we could build up the distribution, indeed, using this data, isn't it? Why not? All nice. But please note that all these points, which I used to build this distribution, may be coming from different hydrometeorological conditions. So we average across everything, put it on one bucket, we shake it, and we get PDF out of it. And this is not what we want. It's all nice for first estimate, but we can do more. Okay, quantile regression is doing a similar thing. We would have forecasted value as in previous plot and observed value, this scatter plot, and quantile regression would calculate quantiles using the same variable. Okay, so it doesn't use other variables, it uses a variable itself to calculate the quantiles of the distribution. What we want is this. We want to build up a model. You remember this whole thing is the same. We want to build here a data-driven model that would forecast PDF and not real value. That's what we want.